I'm sure you'll understand how delighted I am to be here today, and particularly to be talking on a topic that's one that I've been involved with over the years. I want to say a couple of words introducing the BIPM. I'm sure most people here are familiar with what we do, but just start with that. Then I want to trigger some thinking and discussion, I hope, by saying a little bit about what it is we hope to achieve in a international measurement system involving traceability to the SI. I'll articulate some aspects of the vocabulary there with some examples in this particular field. And then, as Martin said, I want to finish by saying something about, I think, what was a landmark meeting for this field, where the BIPM coordinated a conference with the World Meteorological Organization back 3 years ago in 2010. So, a few words about the BIPM. We are an intergovernmental organisation, financed jointly by our member states and associates, and we operate exclusively under the supervision of the International Committee of Weights and Measures, the CIPM. Our mission, which has recently been reviewed and I believe endorsed again, is to ensure and promote the global comparability of measurements. Of course, our interests are with all measurands, not only the measurands that we deal with in our own laboratories, but with all measurands that the National Measurement Institutes and the National Measurement Systems are concerned with. The unique role of the BIPM enables it to achieve its mission by developing the technical and organisational infrastructure of the SI, the International System of Units, and I'll be talking about that as the basis for the worldwide traceability of measurements. And we achieve this in several ways. We have our own laboratory programs that carry out inter-comparisons in the fields of mass, time, electricity, ionizing radiation and chemistry. We have an international staff, and we have a coordinating role whereby we coordinate a network, to use Martin's phrase, of committees covering the scope of the SI and seeking to demonstrate its application and its comparability. To give a scope, idea of the scope of the Meter Convention as of today, the Meter Convention has 54 member states at present and 37 associates of the General Conference. And then we have 51 member states and 36 associates within our mutual recognition arrangement, which covers a quite enormous, I believe, 91 NMIs and 145 designated institutes, as well as 4 international organisations. So, let's move on and talk about the SI and traceability to the SI, why one might want it and what it does for one. These are 2 charts very familiar to those involved in this field. I think we're allowed to say that these are iconic images, if you like. The left one, the very famous Keeling curve, the work of Ralph Keeling of NOAA. Based on measurements at Mauna Loa, he started, it's hard to remember now that when he started doing these measurements in 1960 of atmospheric CO2, he was under real pressure from his funding bodies because nobody thought that was a very interesting thing to do. Then within a year, he started to see a cycle. Within 2 or 3 years, he started to see a trend. And of course, now that is the long-term record that shows what CO2 has done in the atmosphere. We can now do a great deal more than that, and we now have this thing that some people call the flying carpet, which shows how CO2 varies over the years and also as a function of latitude. So we can see the greater variations in the northern hemisphere than in the southern hemisphere. So this data, one should be consoled to know, comes from a network of stations that work within a quality regime. If we look at the data in a little bit more detail there's some Mauna Loa data. You can see that the variations within a year are a few parts per billion, are a few parts per million. In order to get this resolution, the Global Atmospheric Watch project of the WMO have set quality standards for their data, and here are the quality standards for CO2 measurements. In the northern hemisphere, the data quality is required to be within plus or minus 100 parts per billion. That's 0.03% of the average level. And in the southern hemisphere, where the interannual variations are lower, and therefore you can benefit from better resolution of the measurements, it's 50 ppb. So these measurements are done against a target for the quality of the data. That's exactly the sort of things that NMIs are involved in. What's the actual system that's used to produce, to meet those data targets? This is a very simple schematic of how NOAA, who've essentially run the standardization system for 30 years for CO2, how that system works. Basically, the system is, which is the light? Can't get it to work. The system starts in the top right with a series of primary standards that NOAA prepared gravimetrically some 30 years ago. Those standards are verified with the box in the middle, which is an absolute primary manometric system with a repeatability of 100 ppb. But the nature of the way NOAA run the system is that they regard the primary standards as being the source of what they call the scale, and the word scale is very important in this talk. They regard the standards as being the source of their scale, and if you like, they check it against their primary instrument. They then propagate their scale to a set of secondary standards. But those secondary standards aren't the things that go to the field. What goes to the field are samples of real air, acquired there on the left up in the Rocky Mountains. They add some additional components to the real air so that they can cover the range of CO2 that might be experienced by the different stations. And then they certify that air against their standards. And they would refer to this, and I think I would refer to this, as values that are measured against their scale. Well, how well does their scale match up? Stations using some of these NOAA standards have taken part in some of our international comparisons. This is back a few years ago. This is an international comparison of CO2 in air. It indicates what was the state of the art amongst the NMIs at that time. I should say immediately the state of the art amongst the NMIs has improved quite a lot since then. But the point the point I'd like to make is that whereas the results for the NMIs on the left, broadly speaking, have uncertainties of 0.1, 0.2% and degrees of equivalence of 0.1%, these two stations here, measuring against NOAA standards, sit exactly on our line and are meeting the target that they claim, which is an uncertainty of 0.03%. So the system that they use does work, but essentially it's traceability to a scale. But in this case, we see that the NMIs using SI traceability are able to produce comparable data. Okay, well, let's develop the story further by thinking about what one might do with this sort of data. This is a nice diagram taken from a talk given by Andrew Manning at the Royal Society a couple of years ago, and it indicates sort of at high school level what sort of calculations one might want to do about CO2. So one might want to take the Keeling curve up there in the right, and one might want to say that the change of CO2 in the atmosphere is equal to the difference between carbon dioxide emitted and carbon dioxide sunk to biomass and carbon dioxide sunk to the ocean. So that's a kind of interesting study to make. Since one has one measurand and three very difficult unknowns on that chart, one might want to add another measurand that's a little bit easier to measure, which is the change in atmospheric oxygen. Also can be measured, actually rather more challenging than CO2, but one can measure it. And if one puts the oxygen fluxes in there, one can write a second equation for oxygen and say that the oxygen, because we've got stoichiometry, oxygen and CO2 have different molecular weights, the change in oxygen is equal to minus 1.4 times the emission from fossil fuel burning plus 1.1 times the biomass term. So we can add the two together and we can end up with an equation here with two things that we can measure just by measuring gases in the atmosphere and two things that we want to know which are rather difficult to measure. So we're doing an interesting piece of science here. But in order to get the right answer, we're going to have to ask the question, are all of these things measured on the right basis? Are they all measured on the same basis? if we want to be able to do an equation in which we compare measurements of atmospheric CO2 with measurements of atmospheric oxygen, with measurements of emissions to atmosphere from fossil fuel burning, we will surely have to have all of those on the same basis. Now, the property of a measurement system that enables one to compare measurands of different things on the same basis is the term coherence. A measurement system is coherent if we can measure either the same thing in different ways or different things in the same way and produce answers on the same scale. That's coherence. So the property that we need to make this system work is coherence, and I'll go on to show that the SI is a coherent system. But before I do that, let's give another example of a more complicated, perhaps more realistic sort of chart. This is a chart for energy flow in the UK for 2011. One could have put that chart in terms of carbon, of course. I happen to download one that's energy. But if we want this chart to work, we're going to have all the measurements on the same basis. If we measure the fossil fuel energy on a different basis to the natural gas energy or the biomass energy, we won't get measurements on the same basis. So to make all of this thing work, an essential property we need is coherence. Coherence, this is a more formal definition. A system of quantities is coherent when scaling factors do not appear when equations are combined. So you can add together different quantities and you don't have to know that you should have put a scaling factor in, because in the coherent system there isn't a scaling factor. So to make these things work, we're going to have to make them coherent. I use coherence in a slightly broader sense sometimes, but we'll omit that for now. Okay, so that was coherence, but there's a couple of properties of measurement systems that we need to be of use in this field. This chart takes us into the area of temperature measurements. Sometime 20 years ago, I'm sorry the thing on the right's a little bit small, some very simple back-of-the-envelope calculations were done as to what accuracy of temperature measurement one would need to determine whether the atmosphere was warming. This is a little bit dated now because I think things have moved on. But nevertheless, the numbers are still valid. And the answer is that in order to measure atmospheric warming in a 10 or 20 year timescale, you need to have temperature measurements that are stable to within about 0.02 Kelvin. So that sets us a criterion for the stability of our measurement system. But there's more to it than that, because we want to measure this thing all over the world, so we also need all of our stations to be comparable to 0.02 Kelvin. So there are requirements for stability and comparability. So there are three things I suggest that one needs in a measurement system. Measurements that are stable, so we can get long-term trends for decision making. Measurements that are comparable, so that we can put together data from different stations, data from different laboratories on the same chart and know that they're equivalent. But very importantly, and I think very importantly for this discussion, measurements have to be coherent. Results made with different compounds, results made with different measurement techniques, results made by different sectors, thinking in quite different ways, have to be coherent so that they can be brought together. This is a slightly different paradigm to the way environmental monitoring and atmospheric monitoring has generally happened. And I put this slide up because I think it's quite important to understand that although we're making very good headway collaborating with the climate change and the meteorology community, they do use a different language and they do think in a little bit of a different way. And we have to be clear why it is that the SI, I believe, has very big advantages for this field of work, but it doesn't have every single advantage. So let's look at this. The scale approach, which I highlighted earlier, I would say the rationale is that values are disseminated that are traceable to a collection or family of artifacts. So it's stuck associated with a particular set of measurements. It has benefits, and this is something that we must remember in these discussions. It produces data that is very highly consistent because there's a lot of control over where all the traceability is. It's all back to a certain point. So it produces data that is very precise. It's very repeatable. Very good for trends. Very, very good for trends. but it has some disadvantages. There's a sort of operational disadvantage, which is that inevitably all the responsibilities and costs end up with the organisation who have this golden scale in their house. Another disadvantage is that it will be impossible to regenerate if anything happened or if it got used up. And finally, it's probably insensitive to drift in that reference point. I think that's rather important critique. But on the other side of the table, the SI side of the table, where probably we all live and work, values of disseminated are traceable to the SI as realised according to our definitions by our mise en pratique, by our primary methods. It has the benefits. It produces a highly coherent and accurate system. So you can put your electrical power measurements equal to your mechanical power measurements, and they're equivalent. That's part of the work we do to maintain the SI, gives us this coherence. There's a possibility for more than one source, so we don't have to focus all the costs and responsibilities in one place. We can actually share them around, and we have global agreements such as the CIPM MRA, which enable us to quantify and demonstrate that different sources are performing the same way. But you could say it had some disadvantages, one of which is that the values may change in absolute terms within stated uncertainties, but will always improve. What I mean by that is that NMIs, by their nature, improve the quality of their standards. And as we improve our standards, they change very slightly, ideally within the boundaries of our uncertainties, as part of our mission to reduce uncertainties. This is what the environmental and global monitoring community would consider as a disadvantage of our system. But I really think we have to explain that the big advantage of traceability to the SI is that we are working in a properly coherent system. So, I'll move on to talk a little bit about work between the BIPM and the NMIs and the World Meteorological Organization, the WMO. The first thing I want to say in introducing the WMO is that it is an organization that is absolutely steeped in quality and well written and well worked quality systems. This is a rather busy chart indicating some aspects of the quality systems that the WMO operates. If we start in the middle box here, the centre, if you like, of the operations are the stations that are part of the GORE global networks. But in addition to the stations, they have data that comes in from satellites and aircraft. How do they ensure the quality? Associated with each measure round, they have here on the left a set of quality assurance centres. The quality assurance centres are managed by science advisory committees who have globally respected scientists monitoring what they do. Those quality assurance centres put in place calibration centres, they put in place calibration laboratories, and the calibration laboratories have primary standards. So it is a system that is steeped in quality. In March 2010, the WMO came together with the BIPM to organise a conference hosted at the WMO headquarters in Geneva. And the object of that conference was to discuss the measurement challenges for global observation systems for climate change monitoring. It dealt not just with climate change monitoring, it also dealt with some elements of meteorology and numerical weather forecasting. These are the titles of the sessions. I won't go through them all, but you will see just by glancing that they cover the full range of measurands. We're not just talking about gases, we're not just talking about Earth observation, we're talking about ocean salinity, we're talking about the measurands that are essential to make satellite sensors work. The workshop met for 2 days. We had globally recognised experts speaking in each area, and at the end of the 2 days, we brought together a set of recommendations. These have all been published. The reference will come up on the slide in a moment. I can't go through all the recommendations now. They go on for about 12 pages. But I've just put on the screen here 3 of the higher level recommendations. The first one, and this is agreed by both communities, was that the long-term stability and reproducibility of reference materials and explicitly defined calibration scales are critical to the study of temporal change. Exactly what I've just been saying. The property of the stability and comparability of these measurements depends on stable and comparable measurement standards. The WMO, BIPM and academic communities should continue to work together, very important, to increase redundancy through the development of independent approaches. Redundancy is a very important word in that phrase. For a robust measurement system, I indicated that a weakness with the scale system was dependence on a single point of traceability. For a truly robust global system, elements of redundancy are needed. The workshop went on to agree that measurement results should be traceable to the SI where practical. That's a very important conclusion for us in the NMIs. I say WMO willingly came to the table and agreed this. We didn't have to drag them along and force it out of them. They willingly came to the table because they are an organisation that's globally based in quality, as I said. Secondly, the methods and techniques in use for the preparation and dissemination of standards by the two communities differ. I've talked a lot about scales and SI already. Finally, verification. The WMO and the GOR and those scientists involved in producing data related to climate change are very aware of the fact that their results are in the public eye. And they're very aware of the need to produce transparent data verification to show the validity of what they do. And the conclusion here was that the WMO and BIPM communities collaborate to make best use of established national and international infrastructure to meet the requirements for standards. Another key point is the use of established infrastructure, and I hope that will be a theme in discussions throughout these 2 days. It's certainly an essential point of my talk here, that I think in moving forward with Martin's network, the international measurement system applied to carbon, we're talking about applying an existing measurement system to a new challenge. We're not talking about a new measurement system for a new challenge. So after the workshop, the results were all published. There's the web link. I think you'll get these slides and you can download that report from our website. Subsequently also, the WMO signed the CIPM MRA indicating their very firm intention that the agencies that work for them in these quality roles should be fully integrated into our system of producing demonstrable, comparable results. More recently, you probably want to know how things are going in the collaboration. In 2011, it was agreed to form a joint liaison group. There was some suggestion that we might form a formal joint committee, but we felt that within the spirit of using existing infrastructure, we shouldn't set up a new committee. We should work within existing committees. Nevertheless, there's a liaison group which meets annually, which oversees the activities. And the objective of that liaison group is to progress the recommendations through existing structures. An example of an area where the liaison group is seeking to move forward in the near term is on an agreement as to producing evidence as to which of the so-called essential climate variables are well covered by the NMIs and which of the essential climate variables are of most importance to the WMO. So that's a technical point of meeting where we can produce some evidence of what we do, portfolio of what we do, share that with the global monitoring community and enable them to see what the NMIs can do for them. So my conclusions, 3 of them. Firstly, introducing a point I haven't mentioned earlier, but I think is an important point that probably underpins thoughts for many of us here, is the involvement of organisations with long-term core funding is absolutely preferred in this area. There are aspects of standardisation that are delivered by organisations that don't have a continuing mandate. And I think we have to say that grant-funded work may not provide the long-term assurance needed in this particular application field. Secondly, building synergy with existing capability is a cost-effective approach. The SI provides a well-developed and stable basis for traceable measurements. Very importantly, the coherence of measurements that are traceable to the SI is our unique feature and will continue to be very important in this field, and we need to keep articulating that. Established links and relationships provide a blueprint for new collaborations. There are certain areas of our international metrology web where scientists are in good contact with the global monitoring community. Those provide a blueprint for similar relationships in areas where those links aren't yet in place. And finally, international organisations can help pave the way. I think we've shown that with the WMO conference. In particular, links made at the international level can be mirrored at the national level, and in that way, those of us working at the international level can help to open the doors for you nationally. So my final slide, the International Measurement System, I hope I've talked about that, provides the basis for stable, comparable and coherent measurements through traceability to the SI. Thank you very much.